April 1940, and a group of Army Air Corps officers are standing on a tarmac at Republic Aviation's factory in Farmingdale, Long Island. They're staring at something that looks less like a fighter plane and more like someone strapped wings to a giant water heater. The Republic P-47 prototype sitting before them is enormous, absurdly so. While the sleek British Spitfire weighs in at a nimble $5,300, this American beast tips the scales at over $12,000 empty. One officer allegedly mutters that it looks like a milk bottle with wings. And honestly, he wasn't wrong. Republic's chief test engineer, Lyman Bullard, watches their faces fall. He knows what they're thinking because he thought it himself 6 months earlier. The fuselage is so wide that the cockpit sits 7 ft off the ground. Pilots need a ladder just to climb in. The thing is bulbous, ungainly, and looks about as aerodynamic as a barn door. Compared to the nimble Messerschmitt Bf-109s tearing through European skies, this looks like a flying joke. But here's the thing those officers don't understand yet. That grotesque fuselage isn't a design failure. It's hiding the most sophisticated breathing system ever crammed into a fighter aircraft. Inside that fat belly sits a turbo supercharger installation so complex, so audacious, that it would let this milk bottle fly higher than any Axis fighter could ever dream of reaching. The Army brass see a problem. Republic's engineers see a revolution. The timing couldn't be worse for such a radical design. France is about to fall. The Battle of Britain is only weeks away. The Luftwaffe is proving that air superiority wins wars. And here is Republic proposing a fighter that weighs as much as a bomber. Air Force procurement officers are screaming for proven designs. Conventional fighters they can mass-produce immediately. Instead, Republic is asking them to bet on something that defies every assumption about what a fighter should be. Republic's founder Alfred Marchev had actually pitched a much smaller, more conventional fighter called the AP-4 back in 1939. The Army rejected it. Not enough firepower, not enough range. So Republic went back to the drawing board and emerged with this monstrous aircraft. The military wanted 50 caliber machine guns. Republic gave them that. They wanted range to escort bombers deep into Germany. Republic gave them that too. But the price was size, and the size was shocking. Standing next to a P-47, a pilot looked like a child beside an adult. What those skeptical officers couldn't see was the desperation driving Republic's design team. European combat reports were flooding in throughout late 1939 and early 1940. And one fact kept repeating itself. Altitude equals advantage. German bombers were hitting 20,000 ft routinely. Fighters needed to climb above that to dive on them. But how do you make an engine breathe at altitudes where the air is half as thick as sea level? Republic's answer was sitting right there in that bulbous fuselage, waiting to prove everyone wrong. Alexander Kartveli wasn't like other aircraft designers. Born in Tiflis, Georgia, then part of the Russian Empire in 1896, he'd survived revolution, immigrated to France, and eventually landed in America with one obsession burning in his mind. Whoever controls the highest altitude controls the sky. While his contemporaries at Curtiss, Lockheed, and Bell were designing fighters optimized for dogfighting between 15,000 and 25,000 ft, Kartveli was sketching aircraft that could operate at $35,000 ft and above. This wasn't romantic thinking. It was pure mathematics. Kartveli understood something that many military planners in 1940 still didn't fully grasp. Energy fighters beat turning fighters when you start with altitude advantage. A pilot at 35,000 ft holds potential energy. He can dive, convert that altitude into speed, make a firing pass, and zoom back up before the enemy can react. The lower fighter is trapped. He can turn all he wants, but he can't chase an opponent who's 10,000 ft above him. The problem was engine performance. The Pratt & Whitney R2800 double wasp engine that Republic planned to use was a magnificent piece of engineering. 2,000 horsepower at sea level, 18 cylinders arranged in 2 rows, the most powerful radial engine in production. But like every piston engine, it choked at altitude. Air pressure at 30,000 ft is only 1 to 3 of sea level pressure. Feed an engine thin air and it produces thin power. The R2800 would drop to barely 600 horsepower up there. Not nearly enough to power a fighter. Superchargers were the obvious answer, but they came in two flavors, and Kartveli had to choose. Mechanical superchargers, the type used on Spitfires and Bf-109s, were driven directly by the engine's crankshaft. They were compact, reliable, and relatively simple. They also stole horsepower from the engine to run themselves, and they had hard altitude limits. No mechanical supercharger in 1940 could effectively push a fighter above 38,000 ft. Kartveli wanted the other type, turbo superchargers, which promised far greater power at high altitudes. These brilliant devices captured exhaust gases, energy the engine was literally throwing away, and used that waste heat to spin a turbine. That turbine drove a compressor that rammed dense air back into the engine. It was free power in a sense because you were recovering energy that would otherwise blast out the exhaust pipe. And because you weren't mechanically coupling the supercharger to the engine, you could run it at whatever speed was necessary to maintain sea-level air pressure even at extreme altitudes. But turbo superchargers were heavy, complex, and temperamental. They required massive exhaust ducting to channel 700-degree gases from the engine to the turbine at the rear of the aircraft. They needed intercoolers to drop the temperature of compressed air before it entered the engine because compressed air is hot air and hot air is less dense. They demanded intricate oil systems, waste gates to control boost pressure, and regulators to prevent the turbine from spinning itself to destruction. Kartveli didn't care about the complexity. He'd watched the Battle of Britain reports with intense interest throughout the summer and fall of 1940. Luftwaffe bombers were operating at 20,000 to 23,000 ft, and RAF fighters were struggling to intercept them with enough energy left to fight effectively. He became convinced that the next phase of the air war would push even higher, and he was going to build a fighter that owned that realm. General Electric's turbo supercharger wasn't new technology. It had been around since World War I. A brilliant engineer named Sanford Moss had developed the concept back in 1918 at GE's Lynn, Massachusetts facility, proving that exhaust-driven compressors could maintain engine power at altitude. The Army had tested turbo-supercharged bombers throughout the 1930s with impressive results, but nobody had ever successfully packaged one of these beasts into a single-seat fighter. The reason was simple. There wasn't room. A turbo-supercharger system isn't one component. It's an entire subsystem. The GE Type B2 turbo supercharger that Kartveli selected weighed 360 lbs by itself. The turbine wheel inside spun at up to 21,000 RPM, nearly twice the engine's own crankshaft speed. At those velocities, any imbalance, any tiny piece of debris in the exhaust stream could turn the turbine into shrapnel. The exhaust ducting alone added hundreds of pounds. Thick-walled steel pipes had to channel gases hot enough to glow red without warping or cracking. Then there was the intercooler problem. When you compress air, you heat it up. Basic thermodynamics, a simple law of physics. The turbo supercharger would compress incoming air to sea-level pressure, but that compression would raise the temperature to over 300 degrees F. Feed hot air into an engine, and you lose density again, defeating the entire purpose. Kartveli needed intercoolers, heat exchangers that would cool the compressed air before it entered the engine. Those intercoolers required their own ducting, their own airflow, and substantial space. Republic's engineering team spread blueprints across tables in Farmingdale and faced reality. There was no way to fit the system into a conventional fighter fuselage. The turbo supercharger had to sit at the rear of the aircraft as far from the pilot as possible, both for safety and because that's where the exhaust pipes naturally led. But that created a center of gravity nightmare. Stick 360 lbs of turbine at the tail, and you need substantial weight forward to balance it. Solution: put the intercooler in the belly right under the cockpit and run ducting everywhere. The result was that bulbous fuselage the Army officers had mocked. The P-47's body wasn't fat because Republic's designers were incompetent. It was fat because it was essentially a flying plumbing system. Exhaust gases flowed rearward through ducts along both sides of the fuselage. The turbo supercharger sat in the tail, spinning frantically, compressing intake air. That compressed air flowed forward through more ducting to the intercooler under the pilot's seat. Cooled air then flowed back to the engine. Meanwhile, oil lines, fuel lines, hydraulic lines, and control cables threaded through whatever space remained. Alexander Kartveli presented this design to Republic's management in September 1940, and the reaction was split. Alfred Marchev, the company president, saw innovation. The accountants saw disaster. Every added pound meant less performance in other areas. Every additional duct meant more manufacturing complexity. The Army hadn't even committed to ordering the aircraft yet, and Republic was proposing to invest millions in tooling for the most mechanically complex fighter ever designed. But Kartveli had one devastating argument. The alternative was obsolescence. If the air war pushed to 30,000 FT and above, which every intelligence report suggested it would, then conventionally supercharged fighters would become targets, not hunters. The P-47 would own the high ground, and in aerial combat, the high ground is everything. Republic's board understood the stakes and the boldness of Kartveli's vision. Republic approved the design in October 1940. They were betting the company on one engineer's ridiculous supercharger installation. Installing the turbo supercharger system into the P-47 airframe was like performing surgery on a patient while simultaneously designing their skeleton. Republic's engineers weren't just adding a component. They were architecting an entire ecosystem of airflow, heat management, and structural integrity that had never existed in a fighter aircraft before. Start with the exhaust system. The R-2800 engine had 18 cylinders, and each one expelled burning gases at temperatures exceeding 1,700 growler-F. Those gases had to be collected from both cylinder banks, routed through the firewall behind the engine, and channeled rearward without cooking everything they passed. Republic designed two main exhaust stacks, one running along each side of the fuselage, constructed from heat-resistant stainless steel. These weren't simple pipes. They were double-walled ducts with an air gap for insulation, because the aluminum fuselage skin just inches away would melt if directly exposed to exhaust temperatures. The exhaust converged at the tail into a single inlet for the GE B2 turbo supercharger. Inside that unit, the exhaust gases hit the turbine wheel, a precision machine disc with dozens of blades designed to extract maximum energy from the hot gas stream. That turbine was connected by a shaft to the compressor wheel on the opposite side. As exhaust spun the turbine at 21,000 RPM, the compressor wheel on the other end gulped outside air and squeezed it to higher pressure. But here's where things got intricate. The turbine needed a wastegate, essentially a bypass valve that could dump excess exhaust overboard instead of through the turbine. Why? Because as the aircraft climbed, the air got thinner and the turbo had to spin faster to maintain pressure. Without a wastegate, the turbine could overspin and disintegrate. The wastegate was controlled by a regulator system that constantly monitored manifold pressure and adjusted the valve position dozens of times per minute. Pilots called it the automatic pilot for your engine. Now the compressed air, pressurized but dangerously hot, flowed forward through more ducting to the intercooler assembly, mounted in the belly of the fuselage, directly beneath the cockpit. Republic designed an oil-to-air intercooler system, which sounds backwards until you understand the clever engineering. The compressed air flowed through tubes surrounded by engine oil, transferring heat efficiently and keeping the air cool enough to enter the engine safely. That oil was then cooled by ram air entering through ducts in the wing roots, Why use oil as an intermediate step? Because oil has excellent heat capacity and could be pumped to radiators where cooling was more efficient than trying to cool the compressed air directly. The intercooler installation created its own challenges. It added 180 lb to the aircraft's weight, and it sat exactly where the pilot sat. Republic had to raise the cockpit higher off the fuselage than any contemporary fighter. Hence that 7-foot ground clearance that made the P-47 look so ungainly on the ground. But there was no choice. The intercooler demanded that space, and moving it elsewhere would have required even longer ducting runs, adding more weight and more pressure losses. From the intercooler, the now cooled compressed air flowed back to the engine's intake manifold. This return ducting had to be large in diameter to minimize pressure drop. Another reason for the P-47's substantial girth. The entire system created a continuous loop. Outside air entered the compressor at the tail, got pressurized, traveled forward to get cooled, then traveled back to the engine. Meanwhile, exhaust gases made their own journey rearward to spin the turbine before exiting through an adjustable outlet at the very tail. Republic's chief engineer, Roy Burrows, calculated that the complete turbo supercharger installation, turbine, ducting, intercooler, regulators, and all associated hardware added 1,470 seat to the aircraft. That's the weight of a small car crammed into a fighter plane. But those 1,470 toll bought something priceless. The ability to maintain full engine power at altitudes where enemy fighters were gasping. December 1941, and test pilot Lowry Brabham was about to discover whether Alexander Kartveli's obsession was genius or suicide. Brabham wasn't new to experimental aircraft. He'd been flying Republic prototypes since 1939. But the P-47 prototype sitting on the Farmingdale runway represented something entirely different. The XP-47B, as it was officially designated, had completed low-altitude taxi tests and short hops. Now came the real test. Could this beast actually climb to the stratosphere and fight? Brabham strapped into the cockpit on a frigid morning, the kind of cold that makes metal contract and engines reluctant to start. The R-2800 coughed to life with a roar that rattled windows across the factory. He taxied out, ran through his checks, and pushed the throttle forward. The P-47 accelerated slowly. All that weight fought momentum, but at 110 mph, the tail came up. And at 130 she lifted off. Gear up, flaps up, climb, power set. Then Brabham pointed the nose skyward and started what would become a legendary test flight. One that would define the P-47's place in aviation history. At 10,000 ft, the P-47 was climbing at 2,400 ft per minute, respectable for any fighter. Brabham checked his manifold pressure gauge. The turbo supercharger was beginning to work now, compressing the thinning air and feeding the engine what it needed. At 15,000 at ft, most fighters of the era started losing climb performance. The P-47 kept going, 20,000 ft, still climbing at over 2,000 ft per minute. Brabham later wrote in his test report that he kept waiting for the performance to drop off, for the laws of physics to reassert themselves. They didn't. At 25,000 ft, Brabham was higher than most operational missions in late 1941 ever ventured. The air was thin enough that his breath fogged heavily inside the oxygen mask. Outside temperature was 40 degrees below zero. The turbo supercharger was now spinning at maximum RPM, its turbine wheels screaming at 21,000 revolutions per minute, compressing outside air that was less than half sea level density. The engine gauges showed manifold pressure holding steady at 52 in of mercury, exactly what it would show at sea level. The R-2800 didn't know it was 5 mpb high. As far as the engine was concerned, it was still breathing sea-level air at 30,412. Brabham checked his rate of climb, still over 1,500 avatars per minute. This was higher than any Luftwaffe fighter had ever operated in combat. Higher than the service ceiling of the Bf-109E. Higher than the FW-190A. he kept climbing. At 35,000 FT, the world below was a curved landscape of snow and cloud. Brabham could see the curvature of the Earth now, the horizon bending away. His pressurized oxygen system was working perfectly, another innovation Kartveli had insisted on. Without it, Brabham would have been unconscious already. At 38,000 FT, Brabham leveled off and performed a series of test maneuvers. He banked the aircraft, checking control response. The p47 remained docile and controllable. He advanced the throttle to military power and watched the airspeed climb to 375 mph, faster than most fighters could manage at sea level. Then came the moment that would prove Kartveli right. Brabham eased the throttle and let the p47 settle into a cruise at 40,000 forward, 40,000 feet, 8 miles high. The altimeter needle sat there steady, while the engine purred contentedly behind its cowling. Brabham later testified to Army evaluators that at 40,000 FT he could have climbed even higher if needed. The turbo supercharger had more capacity. The engine was stable and performing perfectly. The aircraft was controllable. He flew at that altitude for 15 minutes, performing turns, climbs, and shallow dives, proving that this wasn't just a momentary spike. The p47 could operate at stratospheric altitudes as its normal combat environment. When he finally descended and landed, Brabham climbed out of the cockpit and told the assembled engineers something they already knew but needed to hear. "You've built a fighter that can go where nothing else can follow." The Luftwaffe wasn't stupid. German engineers understood altitude performance as well as anyone, and they'd made their own choices about supercharging technology. But those choices, made in the mid-1930s when the Bf-109 and Fw-190 were designed, had locked them into a ceiling they couldn't break. Understanding why requires diving into the physics that every aircraft designer in World War II was wrestling with. German fighters used mechanically driven superchargers. In a Messerschmitt Bf-109G, for example, a gear-driven impeller sat between the engine and the intake manifold. The engine's crankshaft literally turned this compressor through a series of gears. As the engine spun, the supercharger spun, forcing compressed air into the cylinders. Simple, elegant, relatively lightweight. The entire system added maybe 200 lb to the aircraft compared to the p47's 1,470 lb turbo installation. German fighters stayed lean and maneuverable, but mechanical superchargers had a fatal limitation. They stole power to make power. At sea level, the supercharger on a Bf-109G consumed roughly 150 horsepower just to turn its impeller. Power that couldn't be used to turn the propeller. That's acceptable because the supercharger provides more power than it consumes, resulting in a net gain. But as altitude increases and air gets thinner, the supercharger has to work harder, spinning faster, consuming more power, fighting against diminishing returns. Eventually, you hit an altitude where the power required to drive the supercharger equals the extra power it provides. That's your ceiling. For the Bf-109G with its DB605 engine, that ceiling was approximately 38,000 FT on paper. In practice, by 36,000 FT, the aircraft was barely controllable. The engine was producing so little net power that the slightest maneuver bled energy catastrophically. Pilots couldn't fight up there. They could barely fly. The Fw-190A, designed similarly, faced the same altitude limitations, making it almost impossible to challenge the p47 at extreme heights. Despite being newer and more powerful at low altitude, the Fw-190A actually had a worse high-altitude ceiling because its BMW 801 radial engine with a single-stage supercharger peaked around 34,000 FT before becoming dangerously underpowered. The Germans knew this was a problem. In 1942, they attempted solutions. The Bf-109 G6 OAS received a larger supercharger and was optimized for high altitude, pushing its effective ceiling to 40,000 pfeffers. But this came at brutal costs. The aircraft lost low-altitude performance, and the bigger supercharger consumed even more horsepower, making the plane sluggish throughout its flight envelope. Only a handful were built. Another attempt, the FW-190D, with a Junkers Jumo 2-on-13 inline engine, used a two-stage mechanical supercharger, essentially two compressors in series. This pushed the ceiling to 39,000 safety. But again, the weight and complexity penalties were severe, and it didn't arrive until late 1944. Why didn't Germany adopt turbo superchargers? They tried. BMW and Daimler-Benz both experimented with turbo systems in the late 1930s, but turbo superchargers required exotic high-temperature alloys for the turbine blades, materials Germany increasingly lacked as the war progressed. They required precision manufacturing tolerances that were difficult to maintain under wartime production pressures. Most critically, turbo systems demanded development time Germany didn't have. By 1940, the Luftwaffe needed fighters immediately in massive quantities. Retooling factories for turbo-supercharged fighters would have halted production for months. So, the Luftwaffe stayed with what they knew. Mechanical superchargers were proven, manufacturable, and good enough for the air war they expected to fight. Medium-altitude combat over European battlefields. They never anticipated American strategic bombing doctrine, which would send B-17s and B-24s to 25,000 FT with P-47 escorts cruising above them at 30,000 ETD, waiting to pounce. By the time the Luftwaffe realized they'd made the wrong bet, it was too late. Physics had chosen sides, and the turbo supercharger had won. Spring 1943, and the 56th Fighter Group was about to validate everything Alexander Kartveli had promised. Based at Horsham, St. Faith in England, these American pilots were flying their first bomber escort missions deep into occupied Europe. The 8th Air Force had been getting savaged. B-17s limping home with dead engines and dead crewmen. Luftwaffe fighters hitting them at will. The P-47 the Thunderbolts were supposed to fix that problem, but nobody was quite sure how these fat American fighters would perform against battle-hardened German pilots in their nimble FW-190s and BF-109s. April 15, 1943, provided the answer that would change everything. A formation of P-47s from the 56th was escorting bombers near Antwerp when German fighters appeared. A mixed group of FW-190A4s climbing to intercept. Standard Luftwaffe doctrine was to climb to bomber altitude, make high-speed passes through the formations, then dive away before escorts could respond. Except the P-47s weren't below them. The Thunderbolts were cruising at 32,000 FT, a full 4,000 FT above the bombers they were protecting. Captain Gerald Johnson spotted the Germans first. A dozen fighters clawing for altitude at 28,000 feet, their engines already straining. Johnson radioed his flight and pushed his throttle forward, rolling into a dive. The P-47s accelerated like falling anvils, their weight becoming an asset. By the time Johnson's flight reached the Germans, they were indicating over 450 m/h, faster than the FW-190's maximum level speed. Johnson lined up on a 190, fired a 2-second burst from his 50 caliber guns, and watched pieces tear off the German fighter's wing. The FW-190 snap rolled and went down. Total engagement time, 6 seconds. The surviving Germans tried to climb away, their standard escape maneuver that worked beautifully against Spitfires, which lost energy in vertical flight. But the P-47s just kept coming. At 30,000 FT, with their turbo superchargers feeding the R-2800 engines full boost, the Thunderbolts climbed as well as the German fighters could. At 20,000 feet, Lieutenant Robert Johnson, no relation to Gerald, chased a BF-109G through a climbing spiral that topped out at 35,000 feet. The Messerschmitt finally stalled, its DB-605 engine unable to provide enough power. Johnson fired as the 109 hung in the air nearly motionless. The German fighter came apart. Luftwaffe pilots started reporting these engagements with confusion and frustration. They'd been told American fighters were inferior, heavier, less maneuverable, flown by inexperienced pilots. The maneuverability part was true. The P-47 couldn't turn with a 109 or 190 in a horizontal scissors fight. But the Americans weren't fighting that way. They were using boom and zoom tactics, diving from superior altitude, making one high-speed pass, then zooming back up using their momentum and superior climb rate. German fighters couldn't follow them up, and they couldn't run away because the diving P-47s were faster. By June 1943, the tactical advantage was undeniable. Mission reports from the 8th Fighter Command showed that P-47s were achieving kill ratios of 3.1 and better against Luftwaffe fighters. The secret wasn't just raw firepower, it was altitude, speed, and clever tactics. Pilot skill, though important, wasn't the only factor, even though American pilots were learning fast. It was positional advantage. Colonel Hubert Z.K., commanding officer of the 56th Fighter Group, issued a simple directive to his pilots: never fight below $25,000 fee, unless you had no choice. Stay high, dive on them, climb back up, and make them come to you. The Germans couldn't. Their fighters simply didn't have the power at those altitudes. The Luftwaffe tried to adapt. They sent fighters up earlier, trying to reach altitude before the P-47s arrived, but that burned precious fuel and left pilots exhausted from prolonged oxygen use. They experimented with high-altitude specialized variants, but those aircraft were rare and compromised at lower altitudes, where most combat still occurred. The brutal reality was that the P-47's turbo supercharger had changed the rules of air combat over Europe, and the Luftwaffe had no counter. The Americans owned the altitude, and altitude was everything. But the P-47 supercharger system wasn't just a tactical advantage. It was also a mechanical minefield that could kill pilots who didn't respect its complexity. The same system that gave Thunderbolt pilots altitude supremacy could turn lethal in seconds if something went wrong. And things went wrong with alarming frequency in those early combat months. The most common killer was thermal shock. Remember, the turbo supercharger's turbine was spinning at 21,000 RPM while being blasted by exhaust gases at 1,700 watt-meters. That turbine wheel was manufactured to incredibly tight tolerances. Any imbalance, and it would shake itself apart. Pilots were trained to advance throttles smoothly, giving the turbo time to spool up gradually. But combat doesn't allow smooth throttle movements. You're diving on an enemy fighter. You need power now, and you slam the throttle forward. The sudden surge of exhaust hits the turbine. The temperature spikes, metal expands unevenly, and if you're unlucky, the turbine wheel fractures. The result is catastrophic. The turbine disintegrates at supersonic tip speeds, sending shrapnel through the rear fuselage. Multiple P-47s went down in 1943 with their tails shredded from the inside. Then there was the runaway turbine problem. The wastegate that controlled exhaust flow to the turbine was supposed to be regulated automatically. But the regulator was a mechanical device. Springs, diaphragms, linkages, and it could fail if the wastegate stuck closed. All exhaust went through the turbine. The turbine spun faster. Boost pressure increased. If the pilot didn't catch it immediately and manually override the system, manifold pressure could spike above 70 in, far beyond the engine's design limits. Connecting rods would punch through cylinder walls. Pistons would seize, destroying the engine instantly. In several documented cases, engines literally exploded, spraying oil across the windscreen and starting fires that pilots couldn't extinguish. Lieutenant Colonel Francis Gabreski, who would become one of America's top aces with 28 kills, nearly died from an intercooler failure over France in July 1943. He was at 28,000 out when he noticed his cylinder head temperatures climbing rapidly. The intercooler, which was supposed to cool compressed air before it entered the engine, had developed a leak. Hot compressed air was flowing directly into the engine, raising combustion temperatures beyond safe limits. Gabreski had maybe 60 seconds before the engine seized. He chopped the throttle, dove for thicker air, where the turbo would produce less boost, and nursed the dying engine back across the channel. He landed at the first RAF field he saw, with the engine temperature gauge pegged at its maximum. When mechanics opened the cowling, they found cylinder heads warped from heat stress. The oil system presented its own dangers. The turbo supercharger required oil for lubrication. The turbine shaft was spinning at insane speeds and would seize without proper lubrication. That oil had to be scavenged and returned to the main engine oil tank. But oil lines at the rear of the aircraft operated in an environment of extreme heat and vibration. Lines cracked, fittings leaked. If a turbo oil line failed completely, the pilot might not notice immediately. The oil pressure gauge still showed normal because the engine itself was still getting oil. But the turbo bearing was running dry. Within minutes, the bearing would seize, the turbine would lock up, and all that exhaust energy had nowhere to go. Exhaust pressure would blow seals, crack ducting, and fill the rear fuselage with toxic fumes. Several pilots barely made emergency landings before passing out from carbon monoxide poisoning. Some P-47 pilots started calling their aircraft widowmakers in early 1943. Before Republic and the Army Air Forces worked out most of the bugs, the 78th Fighter Group lost 4 aircraft to turbo supercharger failures in March 1943 alone, more than they lost to enemy action that month. Pilots developed superstitions about the turbo. Some would tap the boost gauge before starting the engine. Others refused to fly aircraft that had just come out of maintenance, preferring planes that had been flying regularly, reasoning that the turbo systems had been proven. The fears weren't entirely irrational. The P-47 supercharger was the most complex system on any fighter in the war, and complexity is always the enemy of reliability. You'd think every Allied nation would be clamoring for a fighter that could operate at 40,000 FRT and outclimb anything the Axis could field. But you'd be wrong. When the British and Soviets got their hands on P-47s for evaluation in 1943 and 1944, their reactions ranged from lukewarm to outright hostile. The reasons reveal just how much national doctrine and combat philosophy shaped aircraft preferences. The Royal Air Force received its first P-47Cs in March 1943 under Lend-Lease. The Air Ministry assigned them to squadrons in Burma and India rather than the European theater, which should tell you something right there. British test pilots at Bosham Down put the Thunderbolt through its paces and filed reports that were diplomatically scathing. Yes, the high-altitude performance was impressive. Yes, the firepower was devastating, but the aircraft was an unwieldy brute at the altitudes where the RAF actually fought. See, British tactical doctrine in 1943 was built around medium and low-altitude operations. The Spitfire Mk9, their frontline fighter, was optimized for combat between 15,000 and 25,000 Arihat. That's where German fighter bombers operated over Britain. That's where RAF fighters mixed it up with Luftwaffe escorts over France. The Spitfire could turn inside anything at those altitudes, and British pilots had spent 3 years perfecting turning combat techniques. The P-47 at 15,000 FT was exactly what American pilots complained about. Heavy, sluggish in turns, and robbed of its key advantage. One RAF evaluation noted that below 20,000 FT, the Thunderbolt handles like a lorry compared to the Spitfire sports car. There was also a practical concern: fuel. The P-47 was thirsty. That big R-2800 engine gulped 100-octane aviation gasoline at rates that shocked British quartermasters. Britain was an island nation that had to ship every gallon of fuel across submarine-infested Atlantic waters. The Spitfire's Merlin engine was significantly more fuel-efficient. Switching to P-47s would have increased Britain's fuel demands by 40% for equivalent operations. The RAF's verdict was polite but clear. Thanks, but we'll stick with Spitfires for Europe. Some P-47s served with distinction in Burma, where their range and ruggedness proved valuable, but the RAF never fully embraced them. The Soviet reaction was even more blunt. In late 1943, the U.S. shipped several dozen P-47D-10s to the USSR for evaluation. Soviet test pilots at the Flight Research Institute flew them extensively and submitted reports that can be summarized as, "Why would we want this?" Soviet tactical aviation was built around low-altitude ground support, not high-altitude air combat. The legendary IL-2 Sturmovik flew missions at 500 to 2500 FT, directly supporting tank columns and infantry advances. Soviet fighters like the Yak-9 and La-5 were optimized for operating below $10,000 fee, where they were nimble and effective. To Soviet pilots, the P-47's high-altitude capability was completely irrelevant. The Luftwaffe on the Eastern Front wasn't flying at 30,000 EBITDA. They were down in the weeds, fighting for survival against overwhelming Soviet numbers. One Soviet pilot's evaluation report noted that the P-47 climbs like a homesick angel, but turns like a freight train. At the altitudes where Soviet fighters actually fought, the Thunderbolt offered no advantages and had many disadvantages. It was heavier, less maneuverable, consumed more fuel, and required longer runways than Soviet fighters that could operate from muddy grass strips just 50 yards behind the front lines. There was a cultural factor, too. Soviet aviation doctrine emphasized simplicity and maintainability. The Yak-9 could be maintained by mechanics with basic tools in field conditions. The P-47's turbo supercharger system required specialized training, precise adjustments, and constant monitoring. Soviet maintenance crews took one look at the complexity and essentially said, "Not yet." The USSR returned most of the P-47s and requested more P-39-era Cobras instead, a fighter that Americans considered mediocre, but which Soviets loved for its low-altitude agility and heavy nose-mounted cannon. The Allied rejection of the P-47 wasn't a judgment of the aircraft's quality. It was proof that Kartveli had designed a fighter for a very specific mission: high-altitude bomber escort over Europe. For that mission, it was unbeatable. For every other mission, there were better options. The British and Soviets knew what they needed, and it wasn't a turbo-supercharged heavyweight built to rule the stratosphere. The P-47's turbo-supercharger didn't just win World War II air battles. It quietly revolutionized how engineers thought about aircraft propulsion for the jet age and beyond. While the P-47 itself became obsolete within a few years of the war's end, the principles embedded in its exhaust-driven supercharger system lived on in ways that still affect aviation today. First, understand what made the P-47 system conceptually radical. Before turbo superchargers, exhaust was waste. Literally hot gas you dumped overboard as quickly as possible. The turbo supercharger proved that exhaust contained enormous recoverable energy. Those 2,500-degree gases spinning a turbine at 21,000 RPM weren't just compressing intake air. They were demonstrating a fundamental principle. You can extract work from exhaust flow. That principle became the foundation of turbine engine design. Early jet engines in the 1940s, like the British Whittle W2 and German Jumo E4, were pure turbojets. Air entered the front, got compressed, mixed with fuel, and burned, then blasted out the back as thrust. Simple but inefficient, especially at low speeds. By the late 1940s, engineers at companies like Pratt & Whitney and General Electric, the same GE that built the P-47's turbo supercharger, started asking a question. What if we used some of that exhaust energy to drive a larger fan, the same way the turbo supercharger used exhaust to drive its compressor? The result was the turbofan engine, which dominates aviation today. A turbofan has a large fan at the front, essentially a turbine-driven propeller inside a duct. Exhaust from the jet core spins a turbine, and that turbine drives the fan. Most of the air that flows through a modern turbofan doesn't even go through the combustion chamber. It bypasses the core, pushed by that big fan. This is called the bypass ratio, and modern airliners have bypass ratios of 10.1 or higher. For every pound of air burned in the core, 10 pounds are accelerated by the fan. The principle is identical to the P-47's turbo supercharger. Use exhaust energy to move additional air. The engineering challenges were similar too. Just as Republic's engineers wrestled with turbine materials that could survive 11600 exhaust, jet engine designers needed alloys that could handle sustained high temperatures. The single-crystal superalloy turbine blades in modern jet engines are direct descendants of the metallurgy developed for turbo superchargers. The cooling techniques, bleeding compressed air through internal passages in turbine blades, were pioneered in part by engineers who had worked on solving turbo supercharger heat problems. There's also a direct lineage in turbocharging for piston engines. After the war, turbocharging technology trickled down to cars. Today, millions of vehicles use exhaust-driven turbochargers to boost engine power. The same principle Sanford Moss developed at GE and Alexander Kartveli packaged into the P-47 is still alive today. That turbocharger spooling up in your car when you accelerate. It's a grandchild of the GE B2 turbo supercharger that powered thunderbolts to 40,000 lift. Even modern high-altitude aircraft owe debts to the P-47 system architecture. The U-2 spy plane, which operates at 70,000 lift, uses turbo-supercharged engines. The concept hasn't changed. Exhaust drives a turbine that compresses intake air, allowing the engine to breathe in the thin stratosphere. The execution is far more sophisticated now, with computer-controlled wastegates and variable geometry turbines, but the fundamental architecture mirrors what Republic's engineers laid out on drafting tables in 1940. Perhaps most importantly, the P-47 proved that extreme complexity could be operationally viable if the performance gain was big enough. Early skeptics argued that the turbo supercharger system was too complicated, too failure-prone, and too demanding of pilot attention. They were right about the complexity. But by 1944, Republic had produced over 15,000 P-47s, and pilots were flying them routinely from forward airfields in Europe and the Pacific. The message to aerospace engineers was clear. Don't avoid complexity. If it delivers capabilities nothing else can match. That philosophy shaped the development of every advanced military and commercial aircraft that followed. From the SR-71 Blackbird to the Boeing 787 Dreamliner, both of which embrace massive complexity to get the performance they need. Alexander Kartveli died in 1974, 29 years after the last P-47 rolled off Republic's production line. By then, his seemingly ridiculous design had been proven right so thoroughly that the numbers alone tell a story of dominance. Republic built 15,686 Thunderbolts between 1942 and 1945, more than any other American fighter. For context, the iconic P-51 Mustang saw only 15,586 built. The P-47 wasn't just competitive. It was the most produced American fighter of the war. But production numbers only hint at operational success. The kill-to-loss ratio shows the tactical advantage the turbo supercharger gave. In European theater operations, P-47s were credited with 3,652 air-to-air kills against Luftwaffe aircraft, while losing 3,499 Thunderbolts to all causes: enemy fighters, flak, operational accidents, and mechanical failures. That's roughly a 1.1 ratio, which sounds okay until you break down the losses. Only 824 P-47s were confirmed lost to enemy fighters. The rest fell to ground fire or accidents. Against aerial opponents, where the altitude advantage really mattered, the P-47 achieved better than 4.5.1 kill ratios. Individual pilots validated Kartveli's design philosophy again and again. Captain Robert S. Johnson of the 56th Fighter Group scored 27 aerial victories, all in P-47s. Colonel Francis Gabreski, also flying Thunderbolts, achieved 28 kills in Europe. These weren't lucky outliers. They were pilots who understood how to use the aircraft's strengths. Gabreski later said in interviews that his tactic was simple. Get above them, stay above them, dive when you have a shot, and zoom back up. The P-47 could do that all day long. German fighters couldn't follow. The altitude supremacy proved decisive in ways beyond dogfighting. By mid-1944, P-47s were routinely escorting bomber formations at 28,000 to 32,000. FT Luftwaffe fighters trying to reach the bombers had to climb through that altitude band where P-47s waited. The psychological effect was huge. German pilots knew that somewhere above them, maybe invisible against the sun, American fighters with altitude and energy advantages were watching. Many Luftwaffe pilots became more reluctant to attack, often breaking off early to avoid the diving thunderbolts. Bomber loss rates dropped a lot. The Pacific Theater told a different story, but reached the same conclusion. P-47s arrived in the Pacific in 1943, and their role shifted toward ground attack. Strafing, bombing, and rocket attacks. The ruggedness from that heavy airframe was invaluable. The R-2800 engine could take battle damage that would down lighter fighters. Pilots discovered the P-47 could survive hits that would destroy a Zero or Oscar. One P-47 pilot, Lieutenant Colonel Neil Kirby, earned the Medal of Honor for a mission where he shot down 6 Japanese fighters in a single sortie while flying a battle-damaged Thunderbolt. The aircraft's weight and strength, first seen as weaknesses, became assets in low-altitude combat. Kartveli never publicly boasted about being right, but he didn't need to. The military's actions proved it. In 1944, when the Army Air Forces studied which fighter to prioritize for production as the war went on, the P-47 stayed in contention alongside the newer P-51 Mustang. The Mustang ultimately won for bomber escort because of its longer range, but the P-47 stayed in full production for ground attack roles through the end of the war. No aircraft that seemed ridiculous in 1940 would still be in massive production 5 years later. After the war, many P-47s served with air forces worldwide. Brazil, France, nationalist China, and others, flying into the 1950s. The final P-47 wasn't retired from military service until 1966, when the Peruvian Air Force finally withdrew its last Thunderbolts. That is a 24-year operational lifespan for a fighter that skeptics said was too complex to maintain and too heavy to succeed. The ultimate proof came from the Luftwaffe itself. In 1945, after Germany surrendered, Allied intelligence teams interviewed captured German pilots and engineers. When asked which Allied fighter they feared most, the most common answer wasn't the nimble Spitfire or the long-range Mustang. It was the P-47. One Luftwaffe pilot's comment, preserved in interrogation records, summed it up perfectly. You couldn't escape it. It could dive faster, climb higher, and it was always above you. We called it Dear Jagger Asterha, the hunter from above. Alexander Kartveli bet everything on altitude supremacy. History proved he was right.